Here, that looks better. Okay. Hello, do we have a speaker on stage? I don't necessarily see.
All right, let's see. I think we're all here.
Okay.
Can you see us? Yeah. Hi, everyone.
Great. Okay, it's not giving me a layout. Alrighty. Well, welcome everyone to PyData Global. Yeah, we're excited to have you all join us today. I hope you all had an opportunity to enjoy the keynote from Peter Wang. As we are giving this session, feel free to chat, to connect with the other attendees here using the chat. If you have any questions for the speaker, then please put them in the Q&A tab, and we will address as many as we can with time at the end of the session. So now it's my absolute pleasure to introduce Tun, who is the VP of Data at Quix. And with that, I think I'll just let Tun take it away with his slides.
Thank you very much, Alice. And hello to everyone joining us today from across the globe for PyData Global. So I hope you're enjoying the conference so far, day 2. So we've got so much more lined up. So thank you for coming to my talk. This one is called Moving from Offline to Online Machine Learning with River. So today I'll be giving an intro to the streaming landscape, going into a bit about what stream processing is and the benefits of online machine learning before moving on to River, which is an open source library that makes it all happen. So first of all, a bit about me. So my name is Shwe, and I'm the VP of Data at Quix. So Quix is a data engineering tools company, and we helped Python developers work with real-time and streaming data. So if you're integrating data that's being created by things like sensors, if you work for in industries such as manufacturing and energy, you'll work a lot with this kind of technology, with technology that produces data in real time. So we help Python developers work with that. So my background is working with high growth startups as a data engineer, and I moved into a kind of head of data and strategic role, so helping companies determine their data and their AI strategy, and where possible, centering it around streaming data first. My areas of interest are around real-time data naturally in the AI ecosystem, and because we work a lot with sensor data, time series data, and industries that have machinery and robots, I work a lot with IoT and Industry 4.0. I believe in the mantra, less is more. I think that things should always be kept simple as possible, and then you build on that complexity later when you know that you need it. And because the ecosystem and the landscape is changing so much, I think that you should always get started sooner. Just always dig in and see what's happening. PyData is such a great way to do that. So many different types of talks, so many things to learn. So it's great to be able to learn all this stuff and get started. So first of all, I'm going to talk a bit about how data is stored. So you're all probably familiar with what a database is. So databases are like relational database management systems. You've got NoSQL databases. What normally happens is you have records, and they're stored as like rows into tables in a database. Now, with streaming and real-time data, it works a little differently. We don't have databases. We have these things called message brokers. So you have the concept of messages that may contain one or many records, and they go into this broker into topics. So tables and topics are kind of similar to each other. The parlance with message brokers is that you write data to a topic by calling it producing to a topic, and you read or query from that broker or that topic by saying you consume from it. So it's producing to topics, consuming from topics. And I'm going to go a bit into the history of the streaming data landscape. So a lot of it was built up using Java technologies. So right in the middle there, you see Kafka or Apache Kafka. And it was created at LinkedIn over a decade ago. And it was used to deal with high throughput data. So this is sort of data that comes in really fast and ordinarily can't be stored in a database, just simply because you won't be able to write to a database quickly enough. So from that, the original team that created at LinkedIn spun out into their own company called Confluent. So there's a product and a platform out there called Confluent Cloud, which gives you a managed Kafka and a way to process all that data. In the bottom right there, you've got a company called Pulsar, which is also an Apache project, which is kind of like a variant on message brokers. In recent years, we've had in the bottom left there a company called Red Panda, which has implemented the Kafka API, so it can be served as a drop-in replacement for any sort of Apache Kafka project. And the same with the top right there, a company called WarpStream, which was later acquired by Confluent. So the thing to point out was that Confluent, Kafka and Pulsar, they were created using Java technologies, so or technologies like Scala that run on the Java virtual machine, the JVM. And you've got companies like Red Panda and WarpStream that came along, and they do things a little bit different. They don't want to do it in Java. So Red Panda, for example, is written in C++, and WarpStream was written in Golang. So what you're seeing is like this is kind of like decoupling away from Java as a landscape for real-time data. And where does that lead us to with data and how companies use data? Well, we know that Python is the predominant language when it comes to data practitioners, whether you're a data scientist, an analyst, or an engineer. When you're working with data, Python's the predominant language for data teams. And we've seen that in industry. A lot of our customers are sometimes, they have Python developers, and sometimes when they don't have Python developers, they have some sort of engineer of some sort, whether they're an electrical engineer or mechanical engineer. They're able to pick up Python much more easily compared to Java. So we see Python, kind of observe Python in lots of different types of teams. The Python data transformation and machine learning libraries have all been really well battle tested as well and proven in production deployments. And these libraries, they're normally rewritten in a JVM language to bring them to streaming use cases. But this always comes with additional complexity. So there needed to be a new way to do this by simply reusing the same Python libraries and applying them in a Python ecosystem to real-time use cases. So this is kind of like where the company I work for, Quix, came in. The background of Quix is an F1 racing background. So the 4 co-founders are pictured there. They worked for a Formula One racing team called McLaren. To localize it, since we're in a global audience, if you don't know what Formula One is, you might be familiar with NASCAR. So it's like quite critical environments, highly competitive environment, because it's you're dealing with race teams. The real-time data processing environments, they are extreme. They're very time critical. You can imagine the speed that these cars go around a track. Any sort of latency is like amplified vastly. It's the difference between getting an insight on time and not getting it at all, and like losing the race. So for them, they have to get these insights really fast. You've got in Formula One in excess of 300 onboard sensors, so you can imagine the throughput of data going through per channel. So how do you deal with that data really quickly? That becomes the problem you've got to solve every day. My background is, as I mentioned, in data. I'm known to get in a racing car now and again as well. The joke is that this is how I got the job for my driving skills rather than my data skills, but we'll see about that. So the 2 products that we work on is an open source library for Python called QuickStreams. So this is a Python API. It's pure Python. And that means that there are no wrappers around other languages. So what some other libraries might do is wrap Python around other languages like Rust, which is a popular one, and also even Java itself. But we're 100% pure Python. We've essentially told ourselves our mission is around Python developer experience. So you get the benefits of things like line-by-line debugging. Like you never develop an application and deploy it immediately to production. You kind of iterate your way there. You kind of build a bit more, debug, build a bit more, debug. And having it in 100% Python makes it really great for newcomers to stream processing. And I'm going to give you some examples of what the API looks like. So we're pushing this idea of streaming data frames. It's reminiscent of the other data frames you may have encountered in libraries like Pandas or PySpark. You kind of access things in a columnar fashion like this. We've also implemented different types of windows for stateful aggregation. So we have tumbling and hopping windows. And only just like last week, we released sliding windows as well. You have access to a high-level state object for custom stateful processing as well. So you can set state in any way that you like. And with Python developers and engineers, you may not want to be concerned with managing infrastructure. So we have Quix Cloud, which helps you to build out these pipelines visually. And yeah, you don't have to worry about Kubernetes, Docker, CI/CD, all that stuff. We manage it all for you. And a lot of developers, they care about the building blocks, of course, the APIs, but they also care about solutions, which is why we also have in one of the menu items, we have this access to templates, which gives you out-of-the-box reference data pipelines that help you to solve problems from the get-go. So yeah, I'm going to show my age a bit. You probably know Marty McFly from Back to the Future. And stream processing is really the core. Stream processing is like the flux capacitor. It's really what makes online machine learning possible. And I'm going to go into the definitions of what offline and batch machine learning is first. So with offline machine learning, I'm going to go into each of these sections. They both utilize machine learning models. Oops, sorry, let's go back. And inference is when you use the machine learning model to make a prediction, and learning is when you train the model by adjusting its weights. So with offline inference, the predictions are generated from batched observations. So what you generally do is you generate many, many predictions at the same time. And these predictions aren't available for real-time purposes. So an example would be, I used to work at a large publisher on a recommender system in my previous workplace. And what we did is we used Spark to process clickstream data to pre-generate recommendations for our users. And these weren't served out in real time. They were instead, the predictions were put into a data store, like a database, and it was put behind an API. Then sometime later, a scheduled job that ran in another team, they would run this job and they would pick these predictions up and then email the users their recommendations. So that is an example of offline inference. For offline learning, this is the most common type of machine learning. So whenever someone says that they have implemented machine learning, this is what they've implemented. It's done in an offline way. It's where you fit a model over static data that has, we call it historical data. So it has a start and an end. So you've grabbed that data and you fitted a model over it. And these observations were all processed in one go to do the training. Let's zoom in a little bit. So with offline learning, you're fitting a model over static data with batches of observations at a time. This normally requires quite a lot of memory because you might be grabbing really large data sets for your training, and that data normally doesn't fit into memory. So that's why you have tools like Spark, which enable you to split up that data. You partition it into much smaller chunks, and you can use parallel workers to process that data and allow it to not run out of memory, basically. It's bounded data, so it's really easy to reason about. With a lot of data sets, you might have seen a lot of data sets where they say, okay, here are all the taxi rides in New York City between the years 2011 and 2012. So that is data that is fixed in size. So it's really easy for us as humans to reason about. So we tend to use that kind of data. There are really well-established processes and tooling around offline machine learning, and I made up that number, 99%, but it seems to fit most use cases. Like it's the most predominant type of machine learning, and this is why data science and batch processing is really intertwined. So let's go into what online streaming machine learning is. And before we do that, let's think about conceptually what the typical journey is of data. So data is generated in real time. So if you think of a user clicking buttons and clicking around a website for generating events for clickstream data, or like pictured here, a robot or some sort of machinery in a plant that has sensors for things like temperature and vibration, like it will take continuous measurements and be generating that data in real time. So these events are getting pushed. They typically stay in motion because they're pushed into that message broker, that type of data store that I mentioned at the beginning. So it goes into a message broker, and then from there, it's pushed into an at-rest state. So it's pushed into a database where it stops moving. And then there's the delay. So sometime later, there's a scheduler that will kick in and it will process that data and it will do it in batches. So that always begs the question of why do you have to put things at rest? Like, why not deal with that data whilst it's in motion? And the usual answer for that is that it's complex and difficult. Kafka is a difficult technology. Dealing with real-time data, dealing with the concept of time is usually a difficult thing to get through. So that's the typical pushback that you get. With online machine learning, I'll go into the same thing. So first of all, for online inference, it's when you take real-time, it's when you make real-time predictions. You use the model to make the predictions when it's requested on demand, and you compute from features where necessary. So you'd fetch these features at the time of request from a feature store. For online learning, this is also known as real-time training. You're fitting a model over streaming data, and what you're doing is you're learning one observation or data point at a time. And online inference is what most people mean when they say they do real-time machine learning. What they're doing is actually just inferring, you're computing that prediction in real time. It's pretty straightforward to do, and it works with batch models because you would have trained a model in batch. So you're using a batch model from offline learning, and you're doing online inference. And it's got a mature tooling ecosystem. There are platforms and tools out there that help you to select the correct model based on certain criteria, and it will serve it out and deal with like the model lifecycle for you. For online learning, this is when you're fitting a model over streaming data, and you're learning incrementally with one observation at a time. So most people don't do this at all. You'll see bidding to how the API works, you might get a label or ground truth come in where you're able to learn on that one data point, or if not, you're going to get a request to make a prediction, and then you'll serve that out. So you'll do it one data point at a time. So it's very much event-based. And with online learning, not all algorithms or models are suitable, and they do naturally work well with unsupervised methods, things that you can, kind of data that you can cluster, sometimes data that doesn't have a label, so it works really well with those kind of methods. It does work well for supervised methods as well, but it requires some thought because you sometimes have a delay for the ground truth. The labels do arrive later, so you've got to design around that. And since data is streamed in, there are many, many unknowns. So things like the number of features, the classes, the cardinality. So each data point that comes in, it can always be the same schema, or it might change schema. It might have the same features, it might be different. Like the classes can change. It's just one of those things you just have to accept as data comes in. The features may appear or disappear over time. The benefits of online machine learning are that historical data isn't needed. It's really great when you don't have access to historical data, or it simply doesn't exist. For example, I've got a Raspberry Pi kit for environmental monitoring and sensing, and these kind of IoT hobby projects in your home are great because you don't have like this backlog of data. You can just get going straight away with predictions. Because you're dealing with one observation point at a time, it requires less CPU and memory. Online machine learning learns one data point at a time, so it has no concept of what the whole data set is. Therefore, it doesn't need to, nor does it want to hold all of it in memory. And the third benefit there is that it adapts to new data and trends. So models are updated as soon as the new data becomes available. And this is fantastic for dynamic environments where data distribution changes over time. And because it's able to adapt so well, it doesn't require retraining. It's just, in fact, continuously being retrained. And you contrast that with batch, where once the data has been fitted to a model, it will need to be retrained from scratch. So what you're normally doing is you're collecting historical data, you're cleaning it, transforming it, creating predictive models. And in the time that it's taking you for that whole process to complete, some new data may have come in. So you'll have to kick off that whole process again to get a fresh model. So that doesn't exist in River because in online machine learning, because you will continuously be retraining. So it's resilient to concept drift. So concept drift is where the underlying distribution in the data changes over time. That is, there are changes in the relationship between the features and the target variable. And what will happen is it will cause a degradation in the model's predictive accuracy. An example would have been the pandemic recently. This would have created concept drift. So with everyone in lockdown and more dependent on online shopping, the best machine learning systems would have been able to adapt to the changing patterns of purchasing behavior. So, a lot of people bought like toilet paper in bulk, for example. The best machine learning systems would have been able to have dealt with those changes. And I've worked on recommended systems in the past, and though it's possible to have ground truth for things like seasonality changes. For example, I know a popular online retailer, they were able to recommend jackets in the colder months. But it's less straightforward for dealing with external changes such as advertising campaigns and economic conditions. The resilience also has applications for sensors and industrial IoT, where you have that natural equipment degradation, things like that, like those robots in a factory, over time they'll degrade and you'll need to figure out when to repair them. So they're really good applications for concept drift, for dealing with that. And the model, last point there, is the stateful ever-changing object, so it's always in flux. And here are some of the use cases. I just mentioned predictive maintenance. It's very important for a lot of the customers we deal with who work in manufacturing with robots and machinery, some of which have very sharp parts and sharp corners. So worker safety is incredibly important. So having predictive maintenance enables you to maintain these machines before they start malfunctioning. And worst off, if you have to take them out of the line, out of the factory, or replace them, that's downtime, and that costs the business money, and it just lowers that output in whatever they're producing. So predictive maintenance is a really, really common use case in those industries. Another thing that we saw that had traction recently is an anti-cheat systems, like in gaming. You're, again, incredibly important to detect cheating in real time so that you can deal with that. That often degrades the environment in a game. Like for multiplayer games, people, the gamers would just start logging off and stop playing the game. So you want to avoid that. So that kind of thing is really important. So for batch and stream, offline and online, what should you do? So I created this meme because, yeah, that's always the question throughout your life. You're always going to get asked, should I pick one or the other, batch or stream? The answer is you should pick both because the reason is batch and stream are complementary. One doesn't replace the other. So you should stream for the current context, and then you should use batch for historical. Like batch usually has better accuracy anyway. Most teams will try to fit streaming into a batch system, but it's much easier to fit a batch into a streaming system. And that's because I consider batch as a specialized subset of streaming, where events are the foundational unit. So when you have events as the foundational unit, you've got a change log of events. So these events can be rewound and played back in order to recreate any historical state whatsoever. I don't recommend this kind of approach. So Nathan Mars coined this Lambda architecture in 2011, where you have double infrastructure basically, and it's dealing with both real-time batch and as well as this mixed type of query, which takes from both. I don't recommend it because you've got to double up on everything. So you've got two code bases, you've got to make sure everything aligns. Your support teams and your platform teams have a lot of fun, so double the fun because you've got double the infrastructure. The one I do tend to recommend is this one where you fit batch into a streaming system. It's called Kappa architecture. It was coined by Jay Krebs, who works at Confluent. He coined it back in 2021. And this is where you have a real-time layer and a real-time app, and you have the batch app, which accesses storage. And the beauty of this is with a lot of companies that need to move data. So once data has arrived in that real-time layer, in that message broker, you're able to sync that. You're able to write that out to many different sources without breaking much of a sweat. So you're able to send it to this database, that data lake, that data warehouse. You're able to do that really easily with little uplifts. So it's a very popular approach. And for the reason being, it's a single core technology stack. It's real-time, and you can recreate historical statements. So there's so many benefits to that. The main benefit being what I mentioned, you don't have to re-architect for new use cases. You basically already have streaming. If you want to slow down the data and save it to a database, you can. So together, it solves all the use cases. So you've got offline, which solves most of the machine learning problems, and you have online, which solves problems where current context is important. So you will probably need both. And there are these two projects that came along to try and solve that, these open source ones you can find on GitHub. So Cream was a project started with the mission of providing pure online machine learning models. And then you had Scikit Multiflow, which was a project specialized in online machine learning models too, but they had also a focus on models that could learn with small batches. So there was a lot of crossover in the mission. So the project leads got together and determined that their focus should solely be on online models that can learn one data point at a time. And so they merged. And this is where River was born, so to speak. So River as a project became a thing. And here are the benefits of River. So you've got a great developer experience. The library was heavily inspired by scikit-learn. Like most data scientists I know have either learned or used scikit-learn, so they're able to pick up River really quickly because there are so many similarities in interplay. It's great for general purpose ML tasks. So you've got regression, classification, unsupervised learning. It's great for ad hoc tasks as well, such as computing online metrics and simple rolling window metrics. You've got lots of different models that are supported as well. So you've got anomaly detection. So you've got a Gaussian scorer, half space trees, one class SVMs, great for time series forecasting. So if you've got sensor data, time series data, with IoT devices, time series forecasting using techniques like Holt-Winters, like completely possible here. These models cope really well with concept drift as well. And lastly, everything is a dictionary. That's the bit that blows my mind because we're used to dealing with vectors in machine learning, but here everything's a dictionary. So I'll show you what that looks like. So here's an example of a data set. So you've got taxi rides in New York City, and we're running a loop just to print it out. You can see the data set looks, it's basically JSON, it's a dictionary. Here's another one. There's a fishing data set. So it's implemented quite a lot of different data sets. So it's able to like grab whatever you need from this library. Loads of data sets are supported. So check it out. All stored as a dictionary. And you've got the models as well. So the models themselves are also dictionaries. So you'll see here, like I'm going through a predicting and then learning phase there, but you can see the model itself is a dictionary. So it means you can version them really easily. You're essentially saving text. And vectorization doesn't exist here because there's no concept of batching things together. You're dealing with them one at a time. So you predict one, you learn one. So this is highly reminiscent of scikit-learn. And you don't have to compute your own metrics. So this is normally what you'd have to do. You'd have to keep an eye on your predicted values and your actual values like this. But with River, you've got a metrics package and you've got several here. I'm just demonstrating the accuracy one here. You can create composable pipelines like this. So here we've got a logistic regression pipeline going that uses that model, and you've got a scaler here. So here you can, I'm using a standard scaler, but there are loads of other scalars, such as a min-max scaler, so that you can normalize your data. And to evaluate model performance, you can use progressive validation, where the target is eventually revealed to the model after it's made its prediction. And this is how you can test the models before you put them into production by introducing this delay so that the ground truth label comes in a bit later. This is representative of real life use cases. Like with clickstream data, you're waiting for an affirmative click, like a trigger that tells you that that user is converted. And this may come in sometime later. And this is kind of like, you can print out the accuracy as well as you're validating it, just so you can see how it changes over time. And last few slides, I'm just going to go through just the documentation for River. It's fantastic. You've got so many different things you can go through. They've got these things called recipes, which will get you started really quickly. I really like the anomaly detection ones, the Gaussian scorers. The half space trees are a type of isolation forest where the anomalies happen quite far apart. So they're really good for anomaly detection, predictive maintenance, things like that. So yeah, I implore you to go and check out River. To get started, you can install the package and you can use loops. But of course, if you want to get a real taste of it in action, you'll need a few components. You'll need a message broker, such as Kafka. You need a stream process as well. I obviously am biased. I think you should use Quick Streams. I think it's the best one for Python developers. So go and check it out. And thank you very much. Here are the links. So please connect with me on LinkedIn if you'd like to know more, or if you want to hang out with other Python Kafka developers. I invite you to join the Slack. So thank you so much for taking the time to join me today, and enjoy the rest of the conference.
Awesome. Thank you so much for the talk. That was great. We do have one quick question. I'm hoping you can answer it quickly. If not, is it usual for such online models to be trained in advance and then continuously trained online? Or how do you handle the bootstrapping of such an algorithm?
Right, yeah. So if you do have historical data, remember, so it's a bit different when you have static data. If you have the actual events, like the logs of the events, like how that data, the deltas essentially on how it changed over time, you can essentially put that through a message broker and replay it. So you're essentially recreating state from at different points in the past. So you've got to think kind of like in 4 dimensions, basically. You've got to think about time. So as long as you have the changes, you're able to recreate that state. It's a little bit more difficult when you have a big one and you're trying to front load it. But if you generally what happens is you have a huge historical fixed data set and you have the changes afterwards. And so you kind of like put them together and it kind of works.
Awesome. All right, so that brings us to the end of the session. Thank you everyone for joining us. Thank you, June, for the great presentation. Enjoy the rest of the conference, folks. Take care. Bye-bye.
Thanks, bye.